Hey folks, let's talk about all the stuff you need to know about test number 2. Just like with test number 1, you're going to have the full lab block to take it. A lot of people do not need the full lab block, so make sure you've brought something to entertain yourself. As long as you stay in the general physics area, you're welcome to wander around, work on what you need to work on. But make sure that you've got something, because otherwise you're just going to be sitting there. The test consists of 15 multiple choice, those are 2 points each, 1 lab-based question for 10 points, and then 5 free response questions, those are 10 points each. Just like last time as well, you can bring a little cheat sheet, 1 piece of paper, front and back, 8.5 by 11, standard notebook size. And make sure you bring your own calculator. Let me know ahead of time if you need one, and I will have one set aside for you. And, by the way, the test is on modules 3 and 4. Modules 3 and 4. But, it's probably helpful to bring the background info you already know from the early parts of class, such as, unit conversions. You need to know how to do that. Metric prefixes. You definitely need to know those. Holy cow, you need to know those. So, it may be good to brush up a little bit on the material at the beginning of the year, but the main crux of this is going to be modules 3 and 4. So let's dive right in. Early on in module 3, we learned all about Newton's 3 laws. The first one is often known as the law of inertia. It basically says that an object that is at rest is going to stay at rest, and an object that is in motion is going to stay in that motion unless acted on by an outside force. Here's another way to think about it. If there is no net force, no grand total force, acting on an object, then the object keeps its exact same velocity. Doesn't matter if that velocity is 0 or a billion or anything in between. If the sum of the forces acting on the object is 0, that object's going to keep its exact same velocity. Newton's second law is kind of the inverse of that. If there is a grand total force on the object, that object is going to accelerate. Now, because acceleration is a change in velocity, that means the object's velocity is going to change. Newton's second law is the holy equation of all things physics. F equals ma, and basically everything else branches off from that. So make sure you've got that down pat. Add up all the forces on an object, set it equal to mass times acceleration. And then Newton's third law. Every action has an equal and opposite reaction. That means if I run up and punch a shovel, the shovel is punching me right back with the exact same amount of force. Typically, Newton's third law does not show up on a free body diagram because you're only looking at the forces acting on one object. Newton's third law does show up if you do a free body diagram for 2 separate objects that are coming in contact with one another. Then I'd see the same magnitude force acting on each of them. Speaking of free body diagrams, in order to successfully draw one, all forces on an object are going to originate from the center. You can basically treat the center of mass as where the forces are basically acting, at least for now. It gets a bit more complicated later, but let's not do that yet. And the forces point in the direction they are acting on the object. Now, notice that I have the word on the object here a couple of times. You only include forces that object is experiencing. You do not include any forces the object is exerting on anything else, right? All we care about is what is this particular thing feeling? Put those forces on, you've got yourself a free body diagram. Also, only include forces acting in the moment. Do not include any, sometimes I call them ghost forces, do not include any past forces. One more important thing about drawing free body diagrams: the direction that an object is moving is not necessarily the direction it is feeling a force. It could be, sometimes, right now I've got my wheelie chair right in front of me. If I give that thing a shove, it will move away from me in the direction that I'm pushing it. Okay, so the force and the motion are in the same direction. That's pretty easy. But that's not always the case. I'm also holding a pen that I'm using to write on this iPad. When I throw it straight up in the air and it leaves my hand, gravity is the only force acting on it. That's pointing down, even though it's moving upward. So when you draw a free body diagram, all you care about are forces, not necessarily the direction the object is moving or anything else like that, just forces. So a few simple tips for drawing free body diagrams. A lot of times, if you try to draw something really neat and fancy, then you can't really see what's going on with all the forces. So it might help to just treat it as a box or a dot, again, at least for now. Typically, when you are drawing a free body diagram and you know which forces are going to be stronger, those are the longer vectors, and the weaker forces are going to be a little bit shorter. And I already mentioned this, but don't include the forces the object is exerting against something else. The types of forces you're probably going to want to include are gravity. This is also known as your weight. The normal force, that's the force where some surface is pushing on an object. Tension, that's if a rope is attached, a rope or a string or something that holds tension. Then there's friction, and that can be kinetic or static. And then you've got different applied forces. If I run up and kick something, the moment that my foot is in contact, you're going to want to include the kicked force. That's just a random miscellaneous force that's going on there. Typically, when you are faced with a force problem, you're going to want to first set up your coordinate frame, decide what location is 0, which way is positive in the y direction, which way is positive in the x direction, and then break all of your forces into x and y components. To help myself stay organized while I do this, a lot of times I make a table of x forces on one column, y forces on the other, and that helps keep things straight in my mind. Then you're going to want to add up all of your x's together and all of your y's together. Again, keeping them separate, so you end up with a grand total x and a grand total y force. And at this point, make sure you don't forget to include negatives. If I say down is negative in the y direction and I've got a downward force, I better slap a negative in front of that while I'm adding them all together. And of course, don't be afraid to leave things as variables. If you're following along whenever I do example problems, I pretty much avoid throwing numbers in until the very, very, very end. It's so much easier to go back and catch mathematical mistakes if you do that. And a lot of times different terms cancel, so that's fewer terms I need to punch into the calculator. The fewer times my hand is hitting a button, the fewer mistakes I can make. If you know the total x force or y force, say something's not accelerating in one of those directions and it's 0, you can set the sum of the forces equal to that value. If you need to find the total force, you can use the Pythagorean theorem to bring x's and y's back together. Once again, once you have your total x force and total y force, you can always and forever set them equal to mass times acceleration in that direction. So the acceleration in the x only, acceleration in the y only. If you have a problem where something is on the ground and it's accelerating forward, but it's not leaving the ground, then I can set the sum of my y forces equal to 0. Because it's not accelerating in the y direction, it's only accelerating horizontally. You are going to need to know how to do some of these ramp problems. Typically, what I recommend doing is putting your y-axis perpendicular to the ramp and putting your x-axis parallel to the ramp. So that'll look a little something like this. My y-axis is right here, and my x-axis is right here. This is super useful because typically, well actually always, your friction force and your normal force are going to be at right angles to each other. Normal is always perpendicular to the surface, and friction is always parallel to the surface. And typically something like this doesn't accelerate off of a ramp. If there's going to be any acceleration at all, it'll probably be up or down the ramp. And wouldn't that be nice to keep the total force only in the x or only in the y direction? So for all those reasons, I recommend setting it up like so. That way gravity is the only force that has both x and y components. Now you're going to want to shift your view a little bit, or at least I like to shift my view a little bit. Basically, I'm going to rotate, if this is the angle theta right here, imagine rotating this entire picture clockwise, an angle theta. Grabbing all my axes and all my forces and running them clockwise, an angle theta. Then I'd basically produce a free body diagram that looked a little bit like this, where all the forces have been rotated. Gravity is no exception. It has been rotated an angle theta away from the vertical where it originally was. So that's going to be right there. Sweet. When you divide gravity into x and y components, gravity's going to have a y component here that is adjacent to that angle. So that means its y component is going to get the cosine. And same sort of thing for the x component. It's now opposite that angle, so it's going to get the sine. That's unusual. So make sure that you've got your SOHCAHTOA rules all down pat so that you can do this sort of thing successfully. But make sure you'd be able to solve a problem about a ramp. We've done it in class, we did it on the WebAssign, and there are some examples where I've worked out the solutions posted on Canvas. So make sure you take a look at those. Ooh, quick clarification thing that a lot of people mix up. Weight versus mass. Mass is just a property of matter. It's just some amount of stuff that matter has. That's in kilograms, and that'll be constant regardless of location. Now, weight is the force of gravity on you. That's the definition of weight. So on Earth, it's just mg. Somewhere out in space, your weight would be whatever Newton's universal gravitation law ends up being for you. That would be your weight. We talked about friction too. Good old friction. Now, static friction, this is when you are just sitting at rest. You are not moving relative to the surface. You are not slipping or sliding or anything like that. You've got static friction acting on you, and that can be a wide range of values. It could be anywhere from 0, if there's no reason for friction to be acting, all the way up to some maximum value, which depends only on the coefficient of static friction and the normal force that's acting on you. As soon as static friction reaches this maximum value, it fails and kinetic friction takes over. Kinetic friction's a bit easier to deal with once you are sliding relative to some surface, sliding or skidding or anything like that. That's kinetic friction that you're dealing with. And it only has one value. It always equals the coefficient of kinetic friction between those two surfaces times the normal force on the object. Now, between any two surfaces, the coefficient of static friction is going to be bigger than the coefficient of kinetic friction. It's a lot more difficult to get something to budge in the first place than it is to keep it moving. Finally, we got to Module 4, which was all about circular motion. First and foremost, we've got period and frequency. Frequency is how many revolutions something makes per second. This would end up having units of inverse seconds, which is also a hertz, H-E-R-T-Z. The period is the amount of time it takes to go around the circle once. So they're complete inverses of each other. How long it takes to make one loop around the circle, or how many loops in 1 second. Complete inverses of each other, so you can find one from the other pretty easily. Now, angular velocity is a measurement of how many radians you have traversed in a given amount of time if you're spinning something in a circle. How many radians per second? Don't forget, in a single circle, there are 2 pi radians. So if I complete a full circle, a full 360 degrees, a full 2 pi radians in one period, I find my angular velocity as simply change in angle over change in time. And since period and frequency are inverses, I could also write it this way instead. Linear velocity is how fast in meters per second something is actually moving. We dealt with linear velocity all through modules 1 and 2. Now for linear velocity, it's distance divided by time. So the total distance I've traveled is the circumference of a circle, 2 pi r, or pi times the diameter. When I take that distance and divide it by time, I get my velocity. Swanky. So because of this, it's related to angular velocity through this equation right here. Don't forget that. That's a super useful one. The linear velocity, how fast you're traveling, depends on your angular velocity and the radius, the distance you are from the center of the circle. Now, if you're moving in a circle, that's only because something is forcing you to go in a circle. Once you add up all of the forces that are either working for or against bringing you into this circle, you can set that equal to the net centripetal force, mv squared over r. A quick note about that. A lot of times when I ask what forces are acting in a certain situation, students will raise their hand and say centripetal force, which, yes and no. Centripetal force is not its own separate force. It's not like, well, we've got gravity, we've got normal, we've got friction, we've got centripetal, we've got tension. It's not a separate category of forces. Instead, it's a grand total right there. So just like we've done for a really long time now, add up all of your forces acting on an object, set it equal to mass times acceleration. Only this time, if that total force is pointing toward the center of a circle and it's making something go in a circle, that means the acceleration is therefore the centripetal acceleration, v squared over r. So take the time to add up all those forces first, then set it equal to ma, and if you can, if you're going in a circle, set that acceleration to v squared over r, and you are golden. Finally, we closed out a bit on Newton's universal gravitation law. This works anywhere in the universe because m times little g, that is very specific just to Earth's surface. This right here, this will work anywhere. It's big G, that's Newton's universal gravitational constant that Newton didn't discover, and it's equal to 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. Take that value and multiply it by the product of the two masses divided by the distance between their centers. Square that distance, and you have found the force of gravity acting on both of them. So Earth is pulling on me with a certain gravitational force. Guess what? I am pulling on Earth with that exact same force. It just affects me a little bit more because I'm less massive. But it's the same number of newtons of force. All right, that's about it content-wise. Now, what gets really interesting is how can you apply all of this information? That's what I look for in the test. So for that, make sure you've got a bunch of practice problems written down. On Canvas in each of these modules, I've done certain examples and typed up solutions. Make sure you take a look at those. Make sure you take a look at last year's test. Hey, why not write up a cheat sheet? Try to take last year's test, see what goes well and what doesn't, and then add whatever else you need to know. And of course, as always, get in touch with me, your lovable physics teacher. Have a good one.